All right. Here we are for the fourth and final free response problem in the momentum packet. This one's from 2002. Woo, bringing out all the recent hits here, I think. Anyway, it says a crash test car of 1,000 kilogram mass moving at a constant speed of 12 meters per second collides completely inelastically. We know what that means. It means they hit and stick with an object of mass m at time 0. The object was initially at rest. Speed v in meters per second of the car object system after the collision is given as a function of time t in seconds by the expression v is 8 over the quantity 1 plus 5t. Calculate the mass of the object. So you're like, okay, we can do this. Okay, so just real quick here, this is part A of our 2002 problem. So here we go. Here we go. So we got this collision. I've got this little toy car, right, moving along, and there's some object of mass m that it's going to run into. So when it hits, it's going to hit and stick. So afterwards, my toy car, crumple, crumple, is stuck to this thing, and together they're moving along, right? We are trying to find the speed v after the collision. Let's see here. This is a crash test car. Yes, did I call it a toy car? Test car. That's 1,000 kilograms. Yeah, most toys aren't 1,000 kilograms. Hits this thing, mass m. Okay, so then here, okay, so I'm going to do a conservation momentum, and I would say, you know, mv plus mv is mv plus mv. Sure. I'm looking like the speed after the collision. Yeah, we're going to assume like immediately after, because as time goes on, it's going to drag on the ground, friction will slow it down and stuff. So you're looking immediately before, immediately after. So at the start, I'm going to actually have 1,000 times that initial velocity, 12 meters per second, plus 0, because this thing is not moving at the start. Afterwards, they're going to hit and stick together, so they'll have the same final velocity. You know what I'm saying? So I can factor out that final velocity, and I'll just have the masses, which is going to be 1,000 plus m times that final velocity. All right. Now I'm looking immediately after the collision. Now the collision is at t equals 0, and this is calculating the velocity after the collision. I'm just going to put a 0 in for t, right? So if I do that at time 0, which is going to be, you know, after the collision here, if I do that, that v is going to be 8 over 1 plus 5t. So that's going to be 8 over 1 plus 0, right? That's just 8 meters per second. That's the velocity immediately after the collision. So that is what I'm going to put into there. So if I do this, I'm going to get 12,000 equals 8 times 1,000. So that's 8,000 plus 8 times m. So doing the math, that'll be 4,000 divided by 8. 4,000 divided by 8. Tell me that's 500. Yes, that'd be 500 kilograms is big M. All right. Let's check it against College Board's scoring guide, shall we? All right. So taking a quick glance at this. All right. It says, first, for any statement of conservation momentum, I'm going to get a point. Okay, which I did here. Bing, bing. Okay. It would have been clear if I said, before and after or something. I hate doing all those little subscripts. So I probably should have just done something like, initial, final. But they would give you the points for this. It's pretty clear I know what I'm doing here. The scores really are not out to get you. They really do want to give you the points. If they can tell you know what you're doing, you're probably going to get the point. Okay, but to be sure, you want to show them what they're expecting. Okay, what they're expecting to see on their little scoring guide. Okay, good enough. Make it as easy as possible for the scorer to give you the points you deserve. That's the guiding principle here. Okay, next, for correctly substituting quantities into the left side, the momentum before, 1,000 times 12 plus 0. Right? Oh, they're just saying names. At mass the car, v the car. Yeah, I see I was really sloppy and quick here. I guess I really should have put some things in here, right? You know what I mean? Mass the car, v the car. Actually, yeah, initial. right? And m times this is 0, and then doing like mass the car plus and made that big M. You know what I mean? And just called this V final. You know, that would have been nicer if I had done that, right? But anyway, good enough. And then they want, so for the values on the left and values on the right, giving you a point for each side. So they would have liked this, is what they would have liked. One for the conservation of momentum, and then one for using labels showing that you know what you're doing. It's true that the values I used kind of showed that that was what I was doing. Like I said, I'd like to think they'd give me the points. AP would. Okay, and the fourth points for the final answer being 500 kilograms. Good enough. So that's 4 points for part A. All right. Part B. Okay. Part B, they say, all right, assuming an initial position of x equals 0, determine the expression for the position as a function of time after the collision. So they gave us v as a function of time. They want position as a function of time. And so for this part, you say, well, I know the relationship between position and velocity. Velocity is how quickly I'm changing position. Velocity is the derivative of the position function. So this is the derivative. To get the position function, I need to integrate. So I am saying that that position is going to be, or like the change in position really is the area under the VT graph. Yeah, integral of VDT. But that would be x minus x naught, and x naught is 0, right? So just my position is going to be that integral of VDT. So I'm going to take the integral of 8 over 1 plus 5t dt, right? Okay, and that'll give. Now I'm not putting bounds because this is meant to be a indefinite integral. So I'm going to get the general expression for any future time t. I guess technically is going from 0 to t, isn't it? Yes, to any future t from time 0. Yes, that is what I should be doing. So it is a definite, but with those bounds. All right, we're good with this, yeah? I think so. So we say, okay, I just have to do this integral. And you say, at this point, I anticipate that for most of you who've seen this in your calculus class already, when I have this with the variable in the bottom, I should be thinking about like, natural logs sort of thing, right? So this would be like the natural log of that denominator, right? Or absolute value of natural log or whatever, that 1 plus 5t. But if this is the thing I took the derivative of to get this, taking this to the minus 1 power, I got to use chain rule. Realize there would have been a 5 kicked out in front. All right, but there isn't a 5. Instead, this is being multiplied by 8, so there must have been a 8/5. Okay, and there's a plus c, right? But the constant is just it's a definite integral here, so the constant's going to go away. So it's just this. All right, that's it. That's going to be my position function. All right. Yeah, that's it, I think. All right, let's check against the AP scoring guide, shall we? All right. Good grief. It's calculus-rific. All right, here we go. They say, first, any indication the velocity is the time derivative of position. Dx dt is this. Okay, again, correctly expressing this above as an integral. I would like to think that if you went right to this, you're showing that you understand. Okay, I don't think I'm sure they would give you both points for that. Showing this shows that you understand that v is dx dt. It's all good. It's all good. I would give me the points for this. Anyway, expressing it, getting an integral form like this, with or without using limits. Yeah, I would give myself the points for both of those. Okay, the relationship between x and t, I think that's good. Okay, then what? I think they were trying to avoid having to write a delta x. Then they say they're going to solve by substituting, doing a u sub here, saying u is the denominator, 1 plus 5t, and then du would be 5 dt. And I can take the derivative of 1 plus 5t. That would just be 5, right? So that's what the du is going to. Never mind. I'm sorry. Forget I said anything. Point is, you're doing this, and they're rewriting this expression in terms of the u and the du, right? And so it's saying, so this is like a 1 over that u, and then the du. Well, yeah, the du is 5 dt, but I got an 8 dt, so there must have been multiplied by a 5/8. I mean, 8/5 to get the 8, right. So yeah, so 8/5 du, yeah. Blah, 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 blah. And so we're getting that out, right? Because the integral of 1 over u du is natural log u. Good enough. We're happy with this. And again, recognizing that at x equals 0, at time 0, and so the constancy has to be 0. Yeah. Correct answer, 1.8/5. Okay, so that's just worth 3 points. Like all the little minutia of the integration here, you'll notice they're not assigning points for because this is a physics class, not a math class. But for recognizing the relationships between position and time, basically they're giving you this point. And then solving by setting up the integral, they're giving you the point 4 here. And then finally your answer. All right, so that's 3 points for part B. All right, which takes us to part C of this problem, which says, now we want to find an expression for the resisting force on the car object system after the collision. Yeah, because afterwards, after the collision, if there wasn't some force resisting, like friction or whatever, this would just go at constant speed. But this speed is not constant. Okay, in fact, as t gets bigger, you can see this v is getting smaller, right? Because the t is in the denominator. I know, I'm pointing at this and you're saying, that's really small font. I can't really read that. Good thing I have a copy of the packet. Anyway, the point is, this is getting slower. As t gets bigger, v gets smaller. So there must be something, it's changing velocity, it's accelerating. There must be something pushing against it to accelerate it, to slow it down, to decelerate it. So we want to find the force as a function of time. And so you say, well, gosh, I want to find force as a function of time. I don't know why I started marking in red. Messing up my color coding. And so you say, well, force in time, that sounds like an impulse to me. But you know what? I don't need to do that. I don't need to do that because here, what they gave me was v as a function of time. Right? And what I'm going to do to find force as a function of time is I can just say F is ma, right? And so the mass of the system I know, the car was 1,000 and the mystery mass m was 500, so that's 1,500, so I know m. If I can find a, I'll find f of t, just multiply by the mass, right? You say, well, a, I got a velocity equation. Oh, acceleration is dv dt. So I just got to take the derivative of this with respect to time, all right? And so you say, well, gosh, taking the derivative of that with respect to time, am I going to really use the quotient rule here? Sure, why not? The quotient rule, you know, that's like low d high minus high d low all over low squared, right? And so that's going to be low d high, the derivative of 8, derivative of constant is 0, minus high d low, the derivative of 1 plus 5t is 5, all over low squared. 1 plus 5t quantity squared. Alrighty, so that's going to be that. Should I have written out derivative of 8 over 1 plus 5t dt? Maybe. Anyway, but you see, so what's that going to be? Times 0, that term's going to drop out. So it's just going to be negative 40 over 1 plus 5t quantity squared. Okay, would be the acceleration. I want the force, so I'm going to take that acceleration and multiply by the mass. So I'm going to say that force is going to be ma. So it's going to be the mass, which is 1,500, because it's 1,000 for the car, 500 for the mystery object, times that acceleration, negative 40 over 1 plus 5t quantity squared. Probably should make that square brackets or something. Okay, what's 1,500 times negative 40? Well, 4 times 15 is 60, so that's going to be 6,000 times 10 more, so it's going to be 60,000. Negative 60,000 over 1 plus 5t quantity squared. Okay, that is my function for the force. That's a function of time. All right, let's check my work. Okay, the scoring guide. All right, says 4 points for this part. First, using Newton's second law. Oh, yeah, to find F is ma. Right, we did that, right? I wrote it. Yeah, okay. Any indication that acceleration is the time derivative of velocity. Hey, look, that's here. All right, and then they set it up, derivative of 8 over 1/5t. They did the derivation. And then for including the minus sign on the final expression for force. So look at that. We get a point for doing that. That's nice. And then proper expression for magnitude of the force, 60,000, negative 60,000 over 1 plus 5t quantity squared. Hooray! Okay, so that's 4 points. Again, why was this negative? Well, because we're pushing against the motion, right? We had positive velocity 12. Our force slowing it down has got to be negative direction. Okay, and sure enough, it calculated out that way. All right. All right, good enough. Hey, that's that part. Now it says here there's an alternate solution. Huh. Okay, that's another way we could have solved this. Any indication that force is the time derivative of momentum. Oh, we could have said F is dp dt. And so we could have just taken our that's kind of silly. We just would have taken the velocity function multiplied by the mass, and then that would have been momentum as a function of time, and then we would have taken the derivative of that momentum function, right? Yes, right? That's what they did. Yeah, force is. Oh, wait, what? Oh, they just went ahead and took derivative of momentum, and they just factored out the m as a constant right away, and they just did Fm times dv dt. That's the same thing we just did. We just took the dv dt and then multiplied by the m here. That's the same. Whatever. I don't know why they even bother with that dp dt part. Okay, good enough. Okay, that's it. Okay, good enough. Okay, that's part C. Okay, one more part. We got part D, and I'm out of room on my paper. Let's see what the question is. Maybe I can squeeze it in here. Determine the impulse delivered to the car object system from 0 seconds to 2 seconds. Oh, of course I can do that. Okay, so here we go. So find the impulse from time 0 to time 2 seconds. Okay, that's going to be fine. Okay, I know. I do not recommend you squeezing stuff in. I say use as much paper as you need. I'm setting a bad example. Okay, here we go. So impulse, integral f dt is my change in momentum. So I could take, I bet there's going to be alternate ways of solving this. I could take this force function that I just came up with, and I could integrate it with respect to time, right? And then once I have that integral, I could do it for bounds from time 0 to time 2. That would be one way of doing it if I really love doing calculus. Okay? There's another way of doing this that's going to be simpler, though. All right? And that would just be, can I calculate the momentum at the end and the momentum at the start and say the change in P, that's the impulse? I'm going to do it that way. You know, not that we're scared of calculus, but I don't know. The change in momentum is the impulse. And so the change in momentum, that's just going to be the mass times the final minus the mass times the initial, right? Okay. We know that our mass is that combined 1,000 plus m plus 500, so that's 1,500 times the final velocity. You say, what's the velocity? It's the velocity at 2 seconds, right? The velocity at the 2 second mark. I can just plug in my equation to find the velocity at 2 seconds. Oh, look, that velocity at 2 seconds, that's 8 over 1 plus 5 times 2. That's 8 over 11. Minus the mass times the velocity at the start. At 0 seconds, we already found that up here, that was 8. Look at that. Look at that. Okay, so if I do that, 1,500 times 8 elevenths minus 1,500 times 8, let's just do that in the calculator. 1,500 times 8 divided by 11 minus 1,500 times 8. And I got minus 10,909. And units are going to be what? Either, if you like, mass times velocity, so it'd be kilogram meters per second, or if you like, impulse is force times time, newtons seconds. Either way you want to put the units, they're equivalent. Okay, so that is my impulse. By the way, makes sense the impulse is negative? Sure, it's going against the motion, force through time, pushing against the motion, slowing it down, taking away that momentum to the right. Yep. Gosh, that's got to be the easiest way of doing this, unless I've made some horrible mistake. Let's check. But like I said, I could also put that force function I just got into here and integrate it from t equals 0 to t equals 2. Why? Let's just do this. Okay, let's see what their solution looks like, their scoring guide. Okay. They say, for a correct expression for the impulse, that's big J, equals delta P, right? Or M times delta V. Okay, giving us a point for that. Okay, for that less. Okay, for a correct substitution in total mass times the V at 2 minus V at 0, right? Times the change in V. That's what I'm doing here. Mass times the final velocity minus mass times initial velocity. So mass times the final minus mass times the initial. That's what I did here. Okay, and look, you see, it ends up being okay. That's V of 2 seconds minus V of 0 seconds. That's just this. Look, 1500 times 8/11 minus 8. Yeah, that's it. Okay, same deal. Yep. So correct substitution's in there, and then correct sign on the final answer. Negative 10,909 kilograms per meter. That's it. Hey, that's 3 points. Woohoo! Okay. Alternately, they said yes for a correct expression, the impulse, integral f dt for J, right? Whatever, and then substituting into this the function you got for force, integrating it dt from time is 0 to time is 2, and then the correct answer, blah blah blah. Yep, I like my way. All right. I mean, and then if you look at this, you say, okay, let's see. 4 points plus 3 is 7, plus 4 is 11, plus 3 is 14. And so look, units point, for correct units on answers to both part A and part D, get a point. Part A, recognize that mass is in kilograms, and part D, recognizing this to be in Newton seconds or kilogram meters per second. Then we get that last point for units. Woohoo! And that's it, 15 points. And that's the 2002 free response problem on momentum.